that tends to happen.
Oh, so cute.
Are those like all engineers?
Yeah, that was my internship when I was at SCE. I was a little like, what was it, senior in college. Let me see if this works. Oh, I also have to.
Patrick, you want to introduce them?
Yeah, you want to, they're on the live cam. So you want to
Oh,
introduce
yeah,
Oh,
we need
okay.
an introduction.
Okay.
So we do have you live streamed.
Oh, okay, perfect. Okay.
Live cams are
So
there.
go down front.
Okay.
Thank you for coming to the first speaker of the year. Let's see. I am proud to introduce Ms. Karlie Garrity, who's going to talk to us about her work on the Southern California Edison Power Grid.
All right, thank you, Patrick. Hi, everyone. My name is Karlie Garrity, and like he said, I am an engineer at Southern California Edison. So to get us started here, who is a freshman? If you could raise your hand. Okay, no freshmen? Okay.
No.
So I guess most of you are seniors, I'm guessing, or, okay, cool. How many of you are looking to do engineering in college? All right, perfect. So the majority of you all. So this will be very relevant. So to start us off, so this is a little bit about my background. I went to Flintridge Preparatory School, which is up the street from here. So to kind of talk about why I decided to do engineering, first of all, my dad is an engineer. He's an electrical engineer. He worked at LADWP for 30 years, and I was really inspired by him, but also I always really cared about the environment. I have a creative side, and I wanted to do something where I could build really cool, impactful things and also contribute to a better environment. So I went into Loyola Marymount with a civil engineering degree. I graduated in 2020, and in 2019, I was applying to a couple of different utilities, and I landed an internship at SCE. So I worked the summer of 2019 in the Civil and Geotechnical Department. I guessed it well because they asked me to stay year-round. So I worked through my last year of university while going to school. So it was quite hard, but I was able to manage that. And during my last year, I was kind of moved around a couple of different groups within Edison. So I really got a feel of like what I like to do. So after civil geotech, I went to substations for a bit, worked there for a couple months, and after that I went to the structural engineering department. So that is where I got my full-time job in structural transmission engineering, so higher voltage structures. And then right after I graduated from LMU, I enrolled for my MBA at Cal Poly Pomona. So those are all the schools I went to, and obviously my company. So a little bit about myself. Okay, so what does Southern California Edison do as a company? Southern California Edison is an electrical utility, and it provides power to much of Southern California. So as you can see here in that little picture, this is all of Southern California territory. Basically, most of Southern California except for that little small dot over there, which is operated by LADWP, and then a little bit of San Diego, and the northern portion is mostly PG&E. So we are 50,000 square miles, and we provide power to 15 million people in Southern California. And power is used to charge phones, power your lights, and your cars, as well as much more. Alright, so let's talk a little bit about how power is generated. So power is generated through a couple of different ways. We have, the Hoover Dam, which is a hydroelectric source, so hydroelectricity. We have windmills, which is a wind energy source, a coal power plant, which is, another source of energy. So at Southern California Edison, we actually are trying to use more green renewable energy sources. That is up to 45% at Southern California Edison. However, across the world, coal-powered plants are quite common. I have a little a statistic over there where 38% of the world is generated with coal-powered plants, which is obviously not ideal. Let me just put this thing down here. Okay, so a little bit about how power is generated. So moving on to the next slide. So how is power created? How does it get to us? So we talked a little bit about generation. So what happens after that? So once the power is generated at that first portion on the far left here, it goes to transmission. So that's where I work. Transmission is high voltage lines. After it is going through those towers, maybe an H-trim or so, it gets to subtrans. So subtrans is your typical substation. That is where electricity is lowered. So we might be going from a 500 kV to 66 kV, and then we have another substation back there where it is converted to distribution. So distribution is typically 12 kV, 16 kV. And then after it gets to the distribution, you know, I'm sure you've seen a lot of those power poles near streets. Those are usually distribution, 16 kV, 12 kV. It is then transported to your home where you can use it for all of those different things. So, okay, perfect. Okay, so I talked a little bit about this, but just to go over it briefly again. So high voltage, 500 kV, 220 kV, mid-level voltage, 115 kV, 55 kV, you know, 66 kV, and then lowest voltage, which is distribution, 12 kV, 16 kV, 33 kV, and power is lowered, or voltage is lowered from high to low through a substation. So on the left here we have a typical substation, lots of transformers, circuit breakers. The middle is where we have transmission towers, which typically carries high voltage transmission lines, and distribution, which carries lower voltage. Oh, yeah.
Will it always go in that order, or will it sometimes be distribution or transmission power as well?
It'll always go from transmission to distribution because typically when power is generated, it's really high voltage. So you have to like step down the voltage to make it safe and usable at someone's house. Any other questions? Perfect. Okay.
How do birds sit on wires and not get electrocuted?
Uh,
Sorry,
they-
this is
yes.
the layman's question.
Yes, yes. Actually, that is quite a big problem at SCE. They, in fact, sometimes do get electrocuted, which is not ideal. But there is a covered conductor, which we have been using for, I guess, birds, but also for wildfire mitigation, which prevents birds from getting electrocuted when they basically sit on it. So, good question. Okay, so what does a structural transmission engineer at Edison do? So basically, what do I do? So basically, I design structures to make sure that they're safe and effective in SCE territory and can handle the loads being applied to them. So the loads being conductors and any sort of wire that goes through the structure. So also, we look at the footings, which are attached to the structure at the bottom. I have a slide I'll show a little bit later on for that. You know, withstanding loads, and making sure that the wires and conductors are safe and good to use, but also making sure that the wires aren't sagging too much. So there's specific clearances from the ground to the wire that we have to adhere by. This is so, you know, when a truck goes by and it's going underneath one of these conductors, it doesn't hit the conductor, things like that. So I do a lot of modeling, a lot of analyses to make sure everything is safe and good to put out into the field.
What do you use to model?
PLS-CAD, another really good question. Yes, PLS-CAD, that is the primary software that we use. And it's pretty extensive. Like we have PLS-CAD, PLS-POL, PLS-Tower. I actually have a couple of slides I'll show, but yeah, very good question. So, another third to this. Okay, that's fine. Okay, so talking a little bit about footings and drilled pure anatomy. So basically footings. So there is another picture. Okay, there we go. So I just wanted to quickly show this. We do design these in Peel's Caisson, and typically what you'll see is a couple feet above the ground at the bottom of a tower. But these footings actually go down 20-30 feet, so they go down quite deep. And the way we determine these, the heights of these footings is we get a lot of geotechnical information. We use our geotechnical group, and they basically tell us the soil properties of the area, and along with like pictures and just like the different water levels that potentially could go through the area, especially for caissons. And then we can design a footing or caisson like this. So, oh,
Do you guys just use concrete for the casing, or do you guys also use like metal rebar and stuff like
yes, so typically outside is the concrete, but we do have a rebar like cage of sorts that goes through in the middle, and they fill it up, and kind of on like the left here you see, like you can kind of see the rebar cage there. Good question.
What does the rebar cage help with?
It just helps like reinforce. I think it's a little bit stronger components than concrete, so making sure like it doesn't break, or even like something that we look out for, especially when I was in civil geotech, for like corrosion or like the breaking of the concrete. A lot of these towers are in really mountainous areas, and so we have to constantly go up the mountains, check and see if the footings are okay, or if it's like, you know, going off of a cliff or something. So definitely things to look out for. Okay, so quick little simple questions here. How many footings are on these structures? So on the first one we have 4 footings, lattice structure. So we got 4 legs there. So the middle, it's called an H-frame. So 2 footings because 2 poles, and then the last one is called a TSP. It has 1 footing.
And so do the footings get like, what's kind of the lifespan of each footing? Do they get sort of maintained like every so often, or is
Yeah.
it sort of more long term?
So I think there's a standard out there that requires planners to look and go out and look at these and make sure they're okay for, I think it's 10 to 15 years, around that lifespan. And there might be a situation where like it's okay and it can, you know, last another 10 years, but they have to at least check every 10 years to make sure everything's okay.
So when you're replacing the footing, do you guys like remove the whole bars and then replace it, or is it just you scrape around and replace it?
I believe it might depend on the situation, but I have modeled caissons where they've just had to completely be redone, especially you know, with our tropical storm. There were situations where caissons would be totally like, this was out in the desert, so a little bit different, but like battered by rocks that came in through like a river of water, and so they had to completely be redesigned in the entire structure. So good question.
So in that case, would you have to remove the entire like line, or would the line be still operational, or would you have to take out the entire like sort of tower?
Yeah, so I think, so this is a lot of our, not planners, but like groundmen and people that go out and like replace the wires, but they have a specific way where they have to de-energize the conductors, but then they like kind of like prop it up and like have it kind of set to the side, and then they put in a new structure and then put it back in. Like it's a whole process. So
But they don't have to take the whole thing down and then replace it and then rebuild it?
in a lot of cases they do have to take down the structure, but yeah, they have ways of like, they de-energize like certain spaces of the line, and then like they'll put in a new structure, and then like have it propped up, and then like put back the conductor into the right spot. So okay, so let's move on to the next. All right, so the right here actually is a little bit about, I have better pictures with PLS CAD, but this is a tower anatomy. So towers are quite complex. There's plenty of different types of towers, but I just wanted to show you know, a little bit about the different portions of the tower. So the middle portion is called the common body. The top red portions are called cross arms. They usually stick out of the tower, they look like little arms, and they hold up our insulators. You have a body extension. This is not always typical, but for taller towers, they usually have body extensions. And then finally, you have leg extensions. And when I used to work in towers, each leg would be called leg A, leg B, leg C, leg D, and this would actually indicate, you know, especially with putting antennas, which I'll also talk a little bit more about later, the direction or the location of where to put things, if there's attachments on the tower. So it helps indicate, you know, just where things are on the tower when, you know, an engineer is looking at a plan of one of these towers. Okay, perfect. So cellular antennas on towers. So when I was an intern, I actually helped with these cellular antenna analyses. So one way SCE makes money, essentially, is they work with cellular antenna companies such as AT&T, T-Mobile, you name it. They pay SCE to put these antennas on towers. It's like a monthly fee, kind of like a rent. And so, but what we have to do is we have to make sure that the TOA, or top of antenna, is low enough so it's not interfering with the conductors or the wires. Another thing we have to look for is making sure that the structure is strong enough to hold the antennas. So we do another PLS-CAD analysis to make sure that the tower is okay. In instances where it's not okay, sometimes we need to add reinforcements or members on the tower to make sure that you know, it's secure. So that's a little bit about antennas on towers. Okay, perfect. Substation work. So
does the electrical, like the electricity going through the lines, interfere with the cell phone signals at all?
I don't think so. I think they have it low enough so that it doesn't interfere with anything. Another thing they have to make sure is when like people are going up to put up the antenna, like they're not close to any sort of electricity. That's like another reason for the TOA, so that when people are working on it, they don't like hit their head on a conductor. Because obviously, like these antenna, I guess cellular companies, they want it as high as possible because they want it to get signal to a lot of places, but we have to make sure that it's low enough so that it doesn't interfere with any electricity. Okay, so moving on to substations, and these are all pictures I took, by the way. Cool stuff. So this was I took when I was an intern in the substations group. I just wanted to show a little bit about it. So on the left here is a typical substation with plenty of circuit breakers. The second to left is a transformer, and you know, we have conductors or wires going to a circuit breaker in the third picture, and then the fourth is an old circuit breaker. A lot of these projects are we replace the older, lesser voltage circuit breakers with new circuit breakers. So I have a quick video I wanted to show that talks a little bit more about substations, because that's not really my expertise, so I'll let this guy explain a little bit better.
We're at the Mariloma substation. This is effectively the southern terminus of all of the TRTV project. This is where we finally bring in all that renewable power. Mariloma brings in power up to 500,000 volts, which is way more powerful than you can use at your home. So we have transformers here that'll step that down to something that's more usable, say something like around 12,000 volts before it actually steps down to about 110 volts in your home. As we're tying in from Vincent down to this facility in Mariloma, what we effectively did is add to the network of parallel lines. By adding this line, it augments that and adds an additional parallel line. So it does increase reliability. I think what's important to take away from this is that this project, again, it's a trend-setting project. It shows what can be done. It shows people that ready access to renewables of this scale is possible. And leading the way in that is a really important part, and that's why I'm really proud to be part of this. To all our customers in our 50,000 square mile service territory, no matter where you are, this renewable power, once it gets into the system, it's available to everybody. So whether you're charging your cell phone, charging your car, flipping on a light switch, making a cup of coffee, you all have ready access to that renewable power.
Perfect. Okay, so just wanted to show a little bit more about substations. Let's see if this works. Perfect. Okay, so I want to now go into conductors. Conductors may okay, I can't say the word. Seem simple from a distance, but they're actually quite complex. The conductors are identified through different weights, diameters, stranding, and amps. So the way we distinguish conductors are actually through bird names. We even have a conductor at Edison called Edison bird. So it's quite interesting. And to get into the next portion, just a little bit, more about what we identify conductors with. Plenty of different variations. So we have hundreds and hundreds of conductors in our system that we use. Okay.
What do some of those words mean?
Yeah,
what is
of course.
Like
thermal coefficient. So those are basically the components to. It gets very technical. So basically, when we design conductors, there's like various just like values. I don't know exactly about thermal coefficient, but I do know I've inputted these values into. I wish I could show you SAG10. It's like they're like numbers super small, and so you basically just input these values. I don't know exactly the electricity component of this, but strength, pretty straightforward. Ampacity, electricity. Non-specular, not really sure about that one either. But shape, weight, and size. That's all just like physical, like civil type stuff. So sorry, that's not the best answer to the question, but okay. Let's move on to covered conductor. Okay, so covered conductor is pretty interesting. The reason for a covered conductor is because we want to prevent wildfires at Edison, or caused by Edison, I guess I should say. So basically anything that hits the conductor, if it's metallic especially, will cause a spark and a potential fire. So we want to prevent that. So in 2020, we added 700 circuit miles of covered conductor. And then in 2022, we added 4,500 circuit miles of covered conductor. So I actually have a quick demo. If we could get a volunteer here to help out with this demo. Anyone? Perfect. Okay, so I guess I can bring this up here. So, oh yeah, it's really simple. So I have a little spoon here. It's a metallic spoon. So how about you touch the covered conductor here? So nothing happens. How about you try the copper conductor on the right side? Do it across with both of the, yeah, perfect. Okay, so this is what happens when a bare conductor touches anything like, say, a metallic balloon out in the just normal everyday life. So bare conductor, covered conductor, thank you so much. I appreciate it, yes. And so this is just a good example of what happens.
I'm glad you didn't get shocked too.
Okay, and so let's see. I actually have a couple of conductor type things to pass around. This is a bare conductor. If you want to pass it, this is a real life conductor that we use out in the fields. And then just to kind of give a comparison, this one's, I don't know if we need to pass this one around, but I do have some smaller like comm wire conductors here. Maybe you want to pass this around too. Much smaller. But yeah, so just different examples. And then we do have a 500 kV conductor here. It's quite heavy, so I don't, probably not pass this around, but maybe I can like hold it up. Let's see. This is our 500 kV conductor with covering on it. It's actually covered conductor. Okay, I'm gonna put this down because it's heavy. But yeah, just a couple of different examples. Okay.
And what is this one is aluminum and stainless steel?
Yes. And I think this was from one of our contractors that we use, but we use the smaller conductor, or I guess I shouldn't say conductors, wires for FRC. Basically, cellular companies, they put their cellular wires going through our line, or like a distribution pole. I'm sure you've seen like on the second layer of a pole. Usually like the black covered wire like that is usually from like a cellular company. Like they add those wires. So that's what that is. Okay, perfect. Thank you. Okay, so let's see if this doesn't run over. Okay, moving on. Okay. So we did our demo. So SCE has been performing wildfire mitigation since 2018. It is believed that we've decreased damage or wildfires from 65 to 70% from 2018 levels, and we've spent quite a bit of money on prevention work. So 1.3 billion in 2020 and 3.5 billion in 2021 and 2022. So just wanted to do a quick video for covered conductor, kind of similar to what we saw, but a real life study that SCE did.
SCE recently conducted a demonstration to show the benefits of insulated wire in high fire risk areas and why power may be shut off during windy, dry conditions. Insulated wire, sometimes referred to as covered conductor, has insulated material covering the bare wire, which significantly reduces the possibility of sparking if foreign objects like tree branches or palm fronds blow into our lines. In this demonstration, we laid out various objects on insulated wire to show that even at high voltages, there was no arcing or sparking on the lines. However, when similar objects were placed on bare wire, the objects started to arc and spark. This is why we implement public safety power shutoffs during high wind conditions when vegetation has dried out. And this is why we are installing insulated wire.
Alright, perfect. So, just another example. Okay. So, when are new structures necessary and how do we go about it? So, a lot of times we need new structures in a couple of different examples. So one being voltage is increased, so the conductors are heavier, so the structures need to be a little bit stronger. Also, covered conductor is heavier, so we do have a lot of projects where we need to replace the structures because of that. Another being that the conductors sag a little bit more, so the clearances that we talked about. What else? So another situation being that there are human causes for damaging, so car hit pole, when a car hits a pole, it causes the pole to fall over. We need to replace that. And then we also have situations such as like hurricanes or earthquakes where we need to go through and redesign our structures. Okay. So when do we, or how do we go about designing just like from the very beginning? So in basically every engineering, I think we have to abide by standards. So the standards that I typically use are typically the TOH. This is for transmission overhead standards. So, but it also has, you know, structure design for H-frames, like how to design basic things with like the spacing between cross bracing and cross arms. And you know, just overall standards. We also abide by GEO 95, so that is a California CPUC, I think, regulated standards. So we, it's California-wide. And then on the electrical side, IEEE. A lot of electrical groups, I imagine, use this one because we're dealing with electricity through the conductors. Okay. So I typically design those H-frame structures up there, and actually on the left here too. So the way this process works is I will be given a certain amount of things. So I'm giving a SPIDA information, a work order map, which is on the bottom left here. So that, you know, tells us basic how to design it with the clearances between the arm and the bracing, the height of the structure, the spacing between like each of the poles. SPIDA tells us if we need any down guys, which are basically like wires attached from like the top of the structure to the ground. Google Earth KMZ, which I'll talk about in the next slide, and then pictures like the one on the right here. Okay, so Google Earth. So Google Earth is especially helpful when, first of all, looking at the locations of the structures we're replacing. So usually we'll get like little pins of where each of these structures are. Another thing it does is it provides locations where there's either high fire or high winds. So we need to implement these different loads into our design. So if there's high fire, say 18 PSF, we need to notate that in our design. And our software actually implements these high loadings, or wind loadings I should say, into our design so we can run the analysis with this load applied. Okay. ArcGIS, somewhat similar. ArcGIS is a little bit different in the fact where it has all the structures in our territory listed out already. So you can literally put in a pole number and it'll pop up with like general information for it. ArcGIS is also really helpful, for high fire risk area zones, which is on the left here. And the red is really high fire, and then the orange is somewhat lower fire risk. And then on the right, you can see the map of transmission lines at SCE owned transmission. So another really helpful software that we use. And then to kind of go back to one of the questions, how do we do analyses for new projects? So we use PLS-CAD. The reason we use PLS-CAD is because you can essentially put in ground information, so really mimic what is out there on real life scenarios, and apply wind loading, just different conditions so that you can really get the best scenario for what will actually happen out in the field. Typically we design the structure in PLS Pole, which I think actually I have on the next slide. So PLS Pole and PLS Tower are software where we design the structures specifically, like one specific structure. Then we go back into PLS Pole or PLS CAD, and we can drop in that structure and analyze it with like the specifications of PLS Pole that we put in. So, you could put this tower in here, or this is a 500 kV model, the same tower out in the field, and then a workaround map for the 500 kV tower. So each thing that you attach, each member has joints. They're all inputted. It's quite complex and sophisticated. And then we have atrium modeling. This is one of the designs I worked on. I do a lot, I think I mentioned before, I do a lot of atrium modeling. So on the left and right, and actually in the back at I think 270 degrees, those are down guys. We put those in, and then the cross bracing, each of the joints have we connect like a brace to it, and then the cross arms, and each of those have different standards, kind of what I talked about before. And monopole modeling, sometimes monopole modeling isn't always required. The reason being is because PLS CAD, you can just put in a stick figure, which is just like a little red line, and it kind of substitutes for a monopole. That's because monopoles aren't really, or poles I guess I should say, aren't really that sophisticated. It's literally just one pole. But it is good for high-level studies when you really want to see how the pole is going to react in a certain situation. Okay, so kind of going into one of our last slides here, another type of work I do are rime ice analyses. So rime ice is typically where there is a lot of snow, a lot of ice in the mountains where it gets colder. We do actually have quite a few mountainous terrains out here, so Where there's poles or lines going through it, we have to analyze to see what will happen in a situation where we get a lot of ice and snow out in the mountains after maybe a storm. So, you know, this is from last year. A pole literally snapped in half after so much ice and snow has been applied to the conductors. So how we do this is we basically design the entire line, all the structures, apply a rime ice loading to the conductor in PLS-CAD, and we see how this structure does. Like if it fails, if we need to put in a new structure, if we need to make the pole taller, stronger, basically just preparing for a future situation or mitigating a past situation in which ice has destroyed structures. So to kind of wrap it up, so there are plenty of opportunities for engineers at Southern California Edison, not only in civil engineering, but also mechanical engineering, electrical engineering, and not even just engineering. You can start with, you know, an engineering background, go into project management. You can do data science, information technology, planning, which is out in the field doing more field work, and we have entire groups for environmental policy, environmental engineering, you know, geotechnical engineering, so you name it. So there's plenty of opportunities wherever you want to go with your career to work at Southern California Edison. So with that, thank you so much. You have any questions? Thank you.
So, my question is, I know that as we progress into having more electric vehicles and whatnot, so that means that there's more demand for energy in our state. I'm believing that Edison doesn't produce a lot of the energy, they provide transmission lines, is that correct?
Yes. Yep.
So as we increase our need for power for Teslas and whatnot, are there limitations in where you can put these transmission lines? For instance, you have to plan out that they can't be X, Y, Z from a city or town. Is there like specifications for all that stuff?
Yes, so that gets pretty complicated, and actually like the civil geotech group does deal with like right-of-ways. I'm trying to recall when I was like 4 years ago when I was doing more of this, but there are situations where like a location is owned by both Edison and you know, whoever owns that area. So there's like right-of-way access to that location, so Edison can go on it. There's areas where you know, obviously it isn't owned, so it gets really tricky. But you're right, you know, with the growing electrical demand and green energy and all that, we're going to have to find ways to add more transmission towers and find more sources throughout Southern California and maybe even beyond. Yes?
So transmission lines for high power, I know they're all mostly overhead. They look like those ant antennas or, you know, alien antennas with the high wires.
Yeah.
Do they ever go underground? Because I know some of our utilities here at Edison, for our streets, the wires are all underground unless you see some older areas developed. Does any of the high voltage lines go ever underground?
There is, so yeah, distribution for sure, especially in like, so putting things underground is pretty expensive. That's another component of engineering that doesn't get talked about too much, at least on my end of the design engineering field, but a lot of, how do I say it, money goes into a lot of these decisions. So especially in well-off areas, you'll see a lot of distribution underground, but it's also pretty tricky to put like 500 kV lines underground. I think actually one of the first, or I think the first in the US, if not the world, 500 kV underground is in Southern California. I actually visited it, but it's pretty dangerous work, especially like for the groundmen. They have to kind of like open up these little holes in the ground and like actually go in to change out the conductor or make sure everything is okay. And this is actually pretty dangerous. You know, you're in a control, like very small environment underground, a little tunnel, and you know, if anything happens, yeah, it's not good. So I think we try to avoid it, but for distribution, I think it's a little bit less risk, and you know, especially in like Laguna, I've heard, maybe around here, we are putting a lot more distribution underground. It's because also I think people don't like looking at electrical structures and conductors, so that's another reason for a push for it. Any other questions?
Why are the lines so far apart on the big towers? Why don't they just all cram them all together?
Yeah, one reason for that is cost. Another reason, cost. Each of these structures, thousands and thousands of dollars. So we do put in structures in the middle. It's called interset poles or structures. This is in a situation where the clearances aren't passing. We put in a bigger conductor, and the conductors are still sagging a little bit too much. So we'll put in like an interset pole in between two structures to kind of raise that conductor up. But we try to spread them out as far as possible, just to avoid having to put too many and avoid costs and just effort for the field guys to go out there. But actually, like, we have even someone in our department who looks at spans over 500 feet. So everything with a span over 500 feet goes to our group to look at, make sure everything is okay, and we don't need to put an interset structure in there. Yes.
Sorry. On some of the transmission lines I see in front of my house, right at the Andrews Crest Highway, sometimes I'll see a helicopter and I guess a lineman on there, and I'm assuming they're looking at the insulation that holds up the cable, or what's the purpose of the guy dangling off a helicopter going from tower to tower?
Yeah, so that's interesting. I know that helicopters are used in areas where it's not easily accessible. Usually they'll go in like the bucket trucks and like lift them up, but like in mountainous terrain, I would assume like maybe it's because it's near like a hill or something. It's just not accessible with like a truck or to go out there, so they'll use helicopters. But yeah, that's pretty rare, so I'm surprised you saw someone there, but that's interesting.
Yeah, I would see it maybe once every 5 years or so.
Wow, okay.
They would go across the tower, but I'm assuming they're just you guys have to service these towers, right?
Yeah.
To get what goes away?
Yeah, reconductoring, that's a huge effort. And also with this cover conductor, there's a lot of, and also upgrading voltage, so like maybe like a higher voltage. Sometimes towers are designed with an expectation that they will be put in like a higher voltage. So like say for example, maybe they'll put in like a 500 kV tower, because each of the different voltages, they have different designs associated with it, and there will be like a 220 kV line going through it. That's because they expect that they might have to replace the conductor with a 500 kV voltage to supply more electricity to like who's living there in the future. So those are a couple of reasons.
My last question.
Yes, of course.
Where is the tallest, I guess, structure body that has to hold the transmission line for Edison?
Ooh, that's a good question. Oh, I actually know the answer to this though. It is at the port of Los Angeles. There are some really, really tall towers over there, and I'm guessing it's because of the cruise ships, but if you ever go to the port of Los Angeles in Long Beach, look out for those really tall structures. They're hundreds of feet tall. It's actually pretty insane. Yeah, good question. Any questions? Great. Thank you.